Solve. We have two forces, 70 newtons and 90 newtons, act on an object. The angle between the forces is 21 degrees. Find the magnitude of the resultant and the angle that it makes with the smaller force. So to find the resultant angle and the resultant magnitude, the resultant is the sum of the two vectors. So we want to put the two vectors down and then add these two vectors together. Now how we put these down depends on a couple of things. First off, since I noticed they want to find out how the sum, the angle between the smaller force and the sum, I'm going to put the smaller force on the x-axis. So here's our xy plane, xy. And our smaller force of 70 newtons is going to be right there, 70. So that, let me call the 70 newtons u vector and v vector. So this is u. And v is 90 newtons and 21 degrees separates them. So here's v. So now that we have these, what they're really asking for is when we add these together, and we can do this visually, if I take u and then add v, I get this vector. This is the resulting vector. So this one is u plus v vector. That's what we want to find. We want to find the magnitude of that vector, the resultant, as well as the angle between that vector and the smaller one, which is perfect. With u in standard position, we will be measuring this angle when we find theta. So now let's put u and v vectors into component form. Another nice thing for putting u on the x-axis is we have a nice u vector equals, this is just 70, 0. The x component is 70 and there's no y component. And v vector, this is going to be in the form of r cosine theta, r sine theta, where theta is measured in standard position. So that's perfect right off of the x-axis. So this will be 90 cosine 21 degrees, 90 sine 21 degrees. So we now have our u vector and our v vector. So with a simple addition of these vectors, we will get our resultant vector. So u plus v vector is going to be 70 plus 90 cosine 21 degrees, comma, and 0 plus 90 sine 21 degrees. This is the resultant vector. So we had 70 plus, so this is the x component plus the x component, and the y component plus the y component. Now, we need to find the magnitude and the angle. Now the magnitude is the square root of the sum of the squares. What I'm going to do is use a calculator to approx these. To find an approximation on our calculator, we type it in and we end up with, I'm going to go to the nearest hundredth, 154.02, comma 32.25. So if you need to pause the video and make sure you can calculate these yourself, please do so. Make sure you're in degree mode. So now the magnitude of u plus v vector is the square root of the sum of the squares of the components. So we have the square root of 154.02 squared plus 32.25 squared. And then we work that out, and then we end up with 157.36, and this is newtons. Okay, so that's the resultant force vector. And then we have tangent theta equals y over x. This is a formula to find the angle. So this will give us theta is arctangent. The y component is 32.25. over the x component is 154.02, and with our calculator this gives us 11.83 degrees. We have found the magnitude and direction. Now this angle is the angle right up here in standard position. So this is exactly the angle from U to the resultant force. Now had you put V below and U above, then we'd be finding the angle from V to resultant force, and we'd have to take that answer and subtract from 21 to get the 11.83. So that's just by putting U on the x-axis, we saved that one step. All right, excellent. Solve the problem. An airplane flies on a compass heading of 90 degrees at 370 miles per hour. The wind affecting the plane is blowing from 318 degrees at 42 miles per hour. What is the true course and ground speed of the airplane? Round results to an appropriate number of significant digits. Okay, we have to first talk about what they mean by a compass heading of 90 degrees. Well, the compass is based on north. So this is not based on the x-axis, this is actually based on the positive y-axis. And then 90 degrees would be 90 degrees to the right. So if we put a quick sketch of this, we would have our vector going to the right. The length is 370 miles per hour, and it is heading 90 degrees, so that's directly east. Okay, now there's also a wind. The wind affecting the plane is blowing from 318 degrees, so it's blowing from 318 degrees. If we measure, starting at north is 0, that would be 0, 90, going clockwise, 90, 180, 270, 318 degrees is in this direction, and it's blowing from that direction. So we have a vector that's going down in this direction into the fourth quadrant. Now we have it's 318 degrees all the way around. Oh, that's not right. Oh, it's not going to let me undo. Fix that a little bit. Okay, good. So this is what's difficult about these bearing problems. It's 318 degrees to there. 318 degrees. So how do we get this angle? Well, that's 180 degrees. So if we do 318 degrees and we subtract 180 degrees, we get 90, let's see, what was it? 138 degrees. So here to here is 138 degrees. We're getting closer. We want this angle. So we take 138 and subtract 90, and we get 48 degrees. So this is negative 48 degrees. Now why negative? Negative because in standard position, clockwise is positive, counterclockwise is negative. So although we're given bearings 90 degrees and 318 degrees, we're converting this to vectors where the x-axis going clockwise is positive measuring angles. So we had to get all the way to this as negative 48 degrees. Okay, so now that we have that, we can set up our vector. So I'm going to do vector of the airplane. This is the one that's going to the right. This is simply 370, 0. And the vector of the wind is going to be an x equals r cosine theta. So r is 42.0, and cosine of negative 48 degrees. The angle based on the standard position is negative 48. Okay, comma 42.0 sine of negative 48 degrees. So that's that's v, the vector for the airplane and vector for the wind. Now what are we after? What is the true course and ground speed of the airplane? So from the parallelogram technique of adding vectors visually, this is actually what we're trying to find, the true airplane course speed. So that's the addition. So we want to add these together. So V sub A plus V sub W is, we will have 370 plus 42 cosine of negative 48 degrees, comma, and 0 plus 42 sine negative 48 degrees. I'm going to go to my calculator and grab a couple of digits here, and I get 398.10 and negative 31.21. So this is the vector of the resulting true course of the airplane. Now we want to find the magnitude and the true course. So now that we have this, we can find the magnitude. By the square root of the sum of the squares. So we have the square root of 398.10 squared plus negative 31.21 quantity squared. And our calculator gives us 399.3 miles per hour. I went to one decimal place as an appropriate number of units, given that we have one decimal place given in the problem. Now, the direction. Theta equals arctangent of y over x. The y component is negative 31.21 over the x component is 398.10, and this gives us negative 4.48 degrees. Now we have to interpret what this negative 4.48 degrees is, and how do we get back to bearing. So we have the angle to the black vector here, negative 4.48. So 4.48 degrees more than the x-axis. So our bearing, given that north is 0, to get to the x-axis, that's 90 degrees. And then we have another 4.48 degrees. So our true bearing is actually 90 plus. I'm having trouble with my pen for a minute, sorry. Trying to fix that a bit. There we go. So our true bearing is going to be 90 degrees plus 4.48 degrees. So we get 94.48 degrees. Alright, so this would be our actual compass heading after the wind has blown us the way it's blown us. And we'd be going 399.3 miles per hour. So given we started at 370, the wind, we have a bit of a tailwind. We were going originally negative 48 degrees, so that was, let's go back to the beginning. So we're going exactly 90 degrees. The wind pushed us essentially 48 degrees more than 90 degrees, but it wasn't a very strong wind. So it ended up pushing us just 4.48 degrees further than where we were headed originally. So a little further south and faster. This completes this problem. A force of 689 pounds is required to pull a boat up a ramp inclined at 16.0 degrees with the horizontal. How much does the boat weigh? So we have horizontal, we have a 16-degree ramp, we have a force, I'm just going to represent it as a block, and the force required to push it or pull it, 689 pounds. And the question is, how much does the boat weigh? Now the weight is going straight down off towards gravity, towards the center of Earth. Now what we need to do is we need to create a new triangle. And this triangle straight perpendicular to the plane, or the ramp. We create a nice right triangle out of this, and we have the vector, sorry, the 689, this is the vector pushing up or pulling, it's pulling, so it would be going up the ramp. We need to figure out where the 16 degrees goes in this triangle. And here's how we do this. So let me draw this in a little bit different way. We have parallel lines. These parallel lines are the actual ramp and this triangle at the bottom. These are parallel. And we have a bisector going through like this. And from geometry we know that these opposite angles are equal. So opposite angles are equal. So on our picture we can figure out 16 degrees from this right triangle here. We can get this angle. This angle would be 74 degrees. 74 plus 16 is 90. So we can get this to be 74. Let me put this up here. This is 74. Because of that, this is also 74 degrees. Put my little degree signs. Okay, now what we're trying to do, let me finish this little triangle, we're trying to get into this triangle. Now there's another rule with geometry, which is the opposite angle right here. So this is 74. So that gives us that this one is 74 degrees. This, you could also go with the parallel lines here and the bisector, this one and this one is 74. Now we get the right triangle. The three angles have to add up to 180. On a right triangle, the two angles have to add up to 90. So we finally get this little piece right in there. That's 16 degrees. So we have recovered, we've created this new picture where that's 16 degrees and that's 689. And the question is, find the weight straight down. This is a simple right triangle. So we could use 16 degrees and use sine, for example, and get opposite over hypotenuse. So we could write sine of 16 degrees equals 689 divided by x. Make a little more room for myself. This gives me x would equal 689 divided by sine of 16 degrees. And computing that with the calculator gives us 2,499.66 pounds. So I imagine the book will say 2,500 pounds. That would be how you find the different weights or forces required on an inclined plane. What is the minimum force required to prevent a ball weighing 19.2 pounds from rolling down a ramp which is inclined 22.6 degrees with the horizontal? So let's start off with our little horizontal and our little ramp. This is 22.6 degrees and we have a weight. Now I'm going to make a larger picture here. The weight goes straight down. The force is parallel to the plane, and that's pretty good right there. And then perpendicular to the plane, we drop that down and we get a nice right triangle. In this case, we know the weight is 19.2. We want to know the force required to prevent the ball. So we want to know the force in the direction of the plane, of the ramp, sorry, along here. So we want to know this force, so that's this force. We've got this weight and we've got this line for the right triangle. Now, so we have, this is 22.6, which would make this add up to 90. This angle is the same as this angle. Those are equal. And the reason for this is parallel lines and bisector. Opposite angles are equal. Since this is the same as this, these two have to add up to 90 because of the right triangle. So that puts this value equal to this value. So we're actually looking at similar triangles. It's just rotated a bit. Okay, so now that we have this is 22.6 degrees, what we really need to do is from this angle get opposite and hypotenuse. That would be a sine. So sine of 22.6 degrees equals x over 19.2. This is x equals 19.2 sine 22.6 degrees. And when we calculate this, we get 7.38 pounds. This is the force required to keep the ball from rolling down the hill. A pilot wants to fly on a bearing of 66 degrees. By flying due east, he finds that a 56-mile-an-hour wind blowing from the south puts him on course. Find the airspeed of the plane. Now there are two distinct ways to do this problem, and one is a right triangle approach. I have an idea about this because we have due east and south, and those are 90 degrees off. And then also, of course, a vector approach. So let's do this in two different approaches. So first one, right triangle. We have a pilot wants to fly on a bearing of 66 degrees. So that would be 66 degrees about in that direction. Pretty close. That's 66 degrees. He wants to fly in that direction. Now, this is complementary. These add up to 90, so 66 and 24. So we can get this as 24 degrees. I always like to get the measurement angle off of the x-axis because that's our standard position that we use in vectors. Now, a wind from the south blowing at 56 miles per hour puts him on course. So if he goes directly east, then a wind pushes him at 56 miles an hour from the south, it puts him on course. So we're looking at the question, find the airspeed of the plane. That's this value. So what he's doing is he's flying directly east. Then the wind is pushing him on course. Okay, so this is actually where the plane is. And then the wind adds him up, and this is where he ends up going. But this is where he's heading, and this is after the wind where he's going. We just have a basic right triangle here, so we can use our SOHCAHTOA. In this case, we'd probably need a tangent because that gives us opposite over adjacent. So tangent of 24 degrees would be 56. Oh, that's not a 50. Try that again. 56 over x, or x equals 56 divided by tangent of 24 degrees. Our calculator computes this to be 125.78 miles per hour. This is the speed of the plane. That's all they were asking for. Now, there's another approach. It's essentially the same picture, but we're going to make the plane and the wind into vectors. So I'm going to call the vector for the plane, how about p vector? This is x comma 0. In other words, we don't know how fast he's going. That's what this question is asking. We know it's going to end up 125.78, at least we hope so, and with this other approach. But it's to the right that far and not up or down. He's flying due east, so there's no y component. And the wind is straight from the south, so it's no x component and it's 56. Now if we add these together, we get x comma 56. Okay, now the angle is 24 degrees, and we get the angle by doing tangent of this. So we would get tangent of the angle. Usually it's tangent theta equals y over x. In our case it's tangent, we know the angle is 24 degrees, equals 56 over x. And now if you take a look at this, you realize this approach is going to give us the exact same answer. Now, the benefit of the vectors approach is if it's not a perfect right triangle, the vectors work out just fine anyway. With the perfect right triangle, we had a little bit faster approach to it. But it's nice to have both techniques in case you don't get a right triangle. This right triangle is very convenient, but the vectors work just fine. All right, excellent.